So each year we tune the sort of both the content and the tempo of the course depending on the mixture. This year we are predominantly STEM people, but I want everyone who is public policy, economics, social sciences, stay put. We've never had a casualty in this course. Everyone has done just great. Austin and Mansuk are going to make sure you get across the finish line with flying colors and honors. On the other hand, I don't want to put our nuclear engineers to sleep, so I'm going to do just a little bit of a brief, kind of a slow-pitch version this lecture of some things that you know very well from any one-on-one Bernstein's nuclear physics course. Okay, so today we're going to last course. Oh, by the way, there's our toolkit from last time. There are some things up there that we haven't talked about. Don't worry about it. We did talk about the speed of light, 300,000 kilometers a second, 3 times 10 to the 8 meters a second. What a mole is, 6.02 to the 23rd. We talked about what an electron volt of energy is. It's 10 to the minus 19th of a joule. Therefore, 1 joule, which is a macroscopic source of energy, is 6.24 10 to the 18th electron volts. That's why we like to develop a convenient language when we talk about atoms and nuclei, such that we're talking about small numbers in a mutually shared language, rather than talking about protons being umpty 10 to the minus 27 kilograms and so forth, which is just kind of silly. We also talked about a kiloton, which is going to be a convenient measure of yield of the nuclear weapon. We said that was 4.18 10 to the 12th joules. Now, where did that come from? Remember that 1 gram of TNT, just by coincidence, happens to be very closely, within about 1% or so, of a kilocalorie. And you remember what a kilocalorie is? What's a calorie? Physical chemistry.
How much energy it takes to raise 1 gram of water by
Right. 1 gram of water by definition is a cubic centimeter. At standard room temperature, if you want to go from 20 something to 21 there, which is like room temperature plus 1.8 degrees in Fahrenheit, how much energy does that take? It takes, interestingly, 4.18 joules. Now, a joule, you might say, you may have a good sense for that. A joule is a Newton meter. So in other words, if I take something that is a spring, for example, that's a spring constant, or there's a constant force I'm pushing against. If I push against something, like a block with friction on it, I push it along the table for 1 meter, and it takes a constant force of 1 Newton. 1 Newton meter is a joule. You remember what a Newton is roughly? It's basically about 1/4 of a pound of force, not exactly that. So another way of looking at this is that then, since it's 4 joules, 4.1 joules per calorie, if I take a pound of weight in my hand and I lift it by 3 feet or a little bit like that, that is roughly a joule. And that amount of energy is enough to heat up a cubic centimeter of water by 1 degree centigrade. Okay. Anyway, so a kilocalorie is 1 gram is is already, so that would be about 4,000 joules. Then a gram to a kilogram is 1,000. A kilogram to a ton is another factor of 1,000. And a kiloton is 1,000 of that. So multiply by another 9 orders of magnitude, and that's where you get 4.2 10 to the 12 joules, equaling a kiloton equivalent yield, and that's the equivalent you think about for nuclear weapons. Okay, we're going to talk a little bit about sizes and shapes of nuclei, and we're going to get into the whole lore of subatomic physics. Question for you, having to do with history of science. Who do you think made the first reasonable estimate for the size of an atom or a molecule? I told you this before. How did you know? You shut up. Okay, so now you all know is Benjamin Franklin. How did he do it? Okay, go ahead, tell us.
Oil droplets on the lake or on various sized pools. He determined, he measured the diameter of the area, surface area across which you would get alterations in reflections on water,
Right.
from oil droplets. And
Yeah. Yeah. It's actually very simple. He actually, as he mentioned, when he went walking in the woods, he'd always he'd have a little thing on the end of his cane. He'd put in something that was sort of like a thimbleful of oil. Let's just say that was a cubic centimeter. And he then goes up to a pond and he dumps the oil in there, and he notices the oil slick that spreads out, spreads. At some point it stops. But does it stop? Yeah, when it becomes a monolayer. If I took a waste paper basket of ping pong balls, turned it upside down, it wouldn't remain in a stack. It would go down, but it stops when you get a monolayer of ping pong balls. Now, oil, of course, has cohesion to it, so in fact, if the molecules just start run everywhere, they do stay chock-a-block as a surface. But if you say, well, 1 cubic centimeter is this area, which I think is a fraction of an acre, half an acre, then you can derive what the thickness of that oil slick is just by conservation volume. That is a rough type for a molecule. Now, oil is a complex molecule, got several atoms in it, but he got the right answer to something on the order of tens of angstroms there. So he actually made an estimate for the size of that. He was a very good scientist. In fact, I think, modern theories of electricity, he in fact is the one who conceived of how you actually get a very rigorous proof of the 1/r squared potential of electromagnetism. He's a really, really good scientist as well as a diplomat. Okay, so here we have it. An atom is we talked about J.J. Thomson's Plum's pudding model, which turned out to be incorrect. The idea that it was some kind of smooth, homogeneous substance, punctuated with little raisins, perhaps of positive charge immersed in negative charge. But it turns out it is something that has kind of an exponentially falling tail. It's a relatively large, amorphous object, largely empty space. But consisting of the number of electrons equal to the number of protons in the nucleus of the neutral atom. And it tends to be on the order of 10 to the minus 8 centimeter, or 100 angstroms. Okay. The nucleus, as we'll talk about the experiments of Rutherford in 1909, 1910, 1911, and where he actually first determined that the nucleus, to his shock and surprise, and everyone's shock and surprise, was a point-like object. It wasn't like the electron, some kind of distributed fluid. It was really a hard point-like object, like the pith of a peach, except much smaller. And he was actually able, in these alpha particle experiments, to determine the radii, the systematic radii of light nuclei, are heavy nuclei, and that these nuclei had kind of a sharp edge to them. Nucleus is about 4 orders of magnitude smaller than that. And for the purposes of this class, you don't need to get into quarks and gluons and so forth. We can just say that it consists of protons and neutrons, those being about 10 to the minus 13 centimeters. which are about 10 to the minus 15 meters. That's a unit we call a Fahrenheit, 10 to the minus 15 meters. Like that. Electrons, for as far as we can tell, are truly point-like. The day may come when we discover that they're composite or have some finite size. But at the highest energies we can achieve, the Large Hadron Collider at CERN and other such experiments, we see no discernible size to the electron. Many things in the history of physics in the past 100 years appeared point-like to us, but as we developed better tools, all of a sudden we discovered they actually had a finite size to them. That story may not be out. Here's the way to think about it. If we had a nucleus the size of a marble right here, the outermost electrons in the atom would be in Rutherford, my other office, across the street, across from Davis, so 100, 200 meters away. Yeah, 100 meters away or so. Okay, here's Rutherford Scattering experiment, and in his to his amazement, he took a very thin film of gold foil. He took a natural alpha emitter, a radioactive source that emitted monoenergetic alpha particles. Typically, alpha particles come out at about 5 MeV kinetic energy. And he then took a zinc sulfide screen. And if you think graduate students are treated badly today, just think that what they were 100 years ago. He had the graduate students in there with a clipboard in a darkened room, kind of like this, watching the zinc sulfide screen. And about every 10 minutes, all of a sudden there'd be a flash of light, and the graduate student C would mark down, a little tick mark there, because he was responsible for the angles of 60 degrees to 70 degrees. And then graduate student D was responsible for watching the little portion of the screen that was 70 degrees to 80 degrees. And I think the union, the graduate student union, would hear about this promptly if we did such things for our students today. And then he made a plot, and he actually was able to plot, discovered the Rutherford Scattering law, or like 1 over sine to the 4th half angle, scattering angle. But then discovered that at some point, when these alpha particles, the trajectory, the classical trajectory is getting too close to the nucleus, all of a sudden that curve eroded, and from that he concluded that at some point the alpha particle got too close and had been captured or absorbed or underwent some other reaction and did not reemerge from that scattering process, and was able to determine the radius of nuclei. And as he said, the fact that he saw alpha particles coming back at extreme angles was like if you fired a 15-inch naval shell with a piece of tissue paper and it came back. It was a great surprise. It was a great discovery in nuclear particle physics. We'll come back to that size of these nuclei in just a second. I think all of you, certainly in chemistry, even know about this. So we designate, when we write down, we designate an isotope. We write down the abbreviation. Here's aluminum, Al. It's to say that it's Z atomic number, i.e. the positive charge, the nucleus positive charge is 13 is superfluous because aluminum by definition is 13, but sometimes it's written down anyway. But then the mass number we write in the upper left-hand corner. That's important to write down because for any given element, there can be multiple isotopes. Most elements have, if not one, then 2, 3, 4, 5 stable or semi-stable forms. We'll look at this in just a second there. And the number of neutrons is simply that number minus the atomic number of 13. Okay, a little bit of semantics. Sorry for the cheesy graphics here. Lithium, for example, has 3 stable or long-lived isotopes of lithium-6, 3 protons, 3 neutrons, lithium-7, 3 protons, 4 neutrons, lithium-8, very short-lived, 3 protons, and 5 neutrons. The isotopes of hydrogen, we have ordinary hydrogen is a proton and electron. Deuterium, where's a very convenient source of deuterium? Yes, well, actually, we put deuterium in our generator, but it actually comes out of seawater, water. And you know to what part, how many parts? Quite common. It's a part per thousand level, something like that. It's easy and cheap to get. Tritium does not exist stably. This is doubly heavy hydrogen. Approximated as a sphere with a reasonably sharp edge. The radius is going up like the cube root of the atomic number. That tells you something, a significant fact about nuclear matter. It's actually suggested on the graph up there. Where's our nuclear entropy?
Let's go back.
Yes, the density saturates even when you're starting at very light nuclei. By the time you get up to medium weight nuclei, the density is constant. As I make larger and larger nuclei, the actual number or the mass per, the number of nucleons per cubic Fermi is relatively constant. So the fact that the radius is only growing like the cube root tells you that nuclear density saturates above a certain mass number. Atoms are not like that at all. In fact, it's astonishing. I mean, when you talk about an atom being basically a cloud of electrons, atoms, as it's going from hydrogen all the way up to gold and lead and uranium, it has kind of a funny behavior due to the shell structure. You actually find that the lead atom is not terribly different in size from a lithium atom. And that's simply because as I increase the number of protons, increase the number of electrons are actually now being compressed. So the actual density of electrons is actually going up because on the main atomic radii are relatively constant. Again, there's a little bit of a sawtooth behavior systematically. Now, the nuclear force is strong and short range, and that range, of course, is about a Fermi, which is characteristic of the size of a proton itself. Radius of a proton, 0.8, 0.9, 0.81 Fermi, something like that. Proton and neutron are not marbles. They tend to be a little bit more exponential in their distribution, but they are very well localized, and they have a radius on the order of about a Fermi. So, in fact, how, just to fill in the history here a little bit, how Rutherford actually determined the systematics. Oh, really?
Yes, on the wall switch.
Okay, thank you. Okay. Thank you. Okay, I may have broken it. So, these were so easy. So here's an atomic nucleus, and then you have, if I can think of these alpha particles, if I just think of these alpha particles cutting in classically, here's the radius of the nucleus, we'll call it R, like that. If we talk about the classical scattering theory, I talk about this being the impact parameter B. So an alpha particle comes in, feels the Coulomb of force, gets repelled away like that. So there's one alpha particle in one of Rutherford's experiments. One that that's kind of a hyperbolic orbit there. Another alpha particle might come in here. And you see it, its closest approach is now larger, so that the smaller the impact parameter, the closer and closer is the alpha particle getting to the nucleus. At some point, for a very sharp orbit like this, all of a sudden, you'll get to the point where that alpha particle will graze the nucleus. And if any impact parameter is smaller than that, in fact, the alpha particle will actually undergo a nuclear scattering. It's and because the force is short range, it's a little bit like if I have a angry dog on a chain that's tied to a stake. You're perfectly safe if you stay 1 inch outside the radius of this chain. Okay, but that's exactly what's going on here. So Rutherford was seeing this famous law. He was looking at the cross section, the differential cross section. We'll talk about cross sections later on. Don't worry about this right now. And he was looking at these measuring these data points, and he's actually seeing the curve fall like 1 over scattering angle, and this thing is going like 1 over sine to the 4th theta over 2. But what he discovers is that at some angle for each nucleus, all of a sudden the curve deviates from this and begins to go down because the alpha particles are getting up. And where this deviation occurs tells him the radius. And he actually does it for lithium, he does it for beryllium, he does it for carbon, he does it for calcium, he does it for gold, and so forth. And then that's where he is able to determine what the radius of this systematically of atomic nuclei across the sphere is going on. Okay. So here are some masses. Again, these are in terrible units that you should not even try to memorize. Electron, 10 to the minus 30 kilograms, 9.1, 10 to the minus 31 kilograms. Proton and neutron, almost the same, 1.67, 10 to the minus 27 kilograms. We'll come up with more convenient units for these just shortly. And here's a very important definition that we're going to make, which is called an AMU, or atomic mass unit. By definition, is 1/12 the mass of a carbon atom. So that's a fully dressed atom, not just the nucleus, but the nucleus with its full complement of electrons. It's very, very light. Each electron is only, in atomic physics units, half of MeV, 0.511 MeV. But by definition, 1 AMU, which we're going to use quite frequently, is by definition 1/12 the mass of a carbon atom. Why did they pick carbon? Who knows? Pretty common. Okay. Two key things: proton and neutron are almost the same mass, but importantly, they are a little bit different. The neutron is actually heavier, and the proton is roughly 2,000 times heavier. Okay, masses. Okay, so here's some. We're going to purge out of your mind crazy numbers that have 10 to the minus 27 or 10 to the minus 31 in them. And we're going to speak in sort of atomic/nuclear units. So a proton, you can think of a proton and neutron being roughly a GeV. Proton 938.7 and neutron 939.56. So you see it's actually about 1.7, 1.8 MeV difference, or no, 1.3 difference between the two of them, with the neutron being heavier. Okay, so this is going to be something that will be important for you to use. We'll actually have you in a problem set, do some very, very simple numbers. In the nuclear data tables, in the chart of nuclei, rather than talking about the absolute mass of a nucleus, we normally talk about the mass excess. There's actually 3 different ways of describing the mass of the nucleus. 3 or 4 common ways. This is the one we use the most. And it goes as the following. A is always an integer. It is the atomic number is the number of protons. What's A called? Atomic mass, I guess. Okay, it is an integer. Okay, 1, 2, 3, 4, 5, all the way up. Uranium is 238, and so forth, like that. The mass in AMU units minus this will be how much does that deviate if every nucleus in the periodic table had the same binding energy as a carbon nucleus, then in fact this delta would be 0. Okay. It turns out these numbers are this number very slightly higher or very slightly lower than this number, which is a way of describing the mass of the nucleus. You could put it this way. I could tabulate everybody in this room, and you say, this gentleman here is 71 inches tall. This woman over here is 66 inches tall. This person here is 68 inches tall, and so forth. And so I could describe accurately everybody's height by their absolute level from the floor up to the top of their head. I could say, alternatively, just pick a random number. You could say a average size person is going to be 66 inches tall, and describe everybody. I could tabulate people then by the difference between their height and 66. So this person in that table would be +6. This person would be 0. That person would be -2. This person would be +7 or something like that. The mass excess is just simply using a carbon-12 nucleus with its binding energy is kind of the standard against which deltas are measured. You get, when you do calculations, you get the same answer one way or another. It can't make any difference, as we'll see in shortly when we calculate the value of the reaction. So we went through this, and I think you basically got it right. I asked the question, do 4 separated nucleons weigh more or weigh less than the 4 of them put together into a bound nucleus? The answer is left or right?
They weigh more.
Exactly, right. That's the statement of Einstein that the equivalency of mass and energy, which means to say that the state on the left actually of 4 individual nucleons is a state of higher energy than the bound state here, which tells you something interesting, and that is that when nucleons aggregate, reactions occur to actually cause bound states of complex nuclei. Somehow energy is given off, and that's something that you can harness. So when you have a state of less binding energy to more binding energy, that's like money in the bank. That's something you can profit from. That's something that can give you energy for powering something or making something go pop like that. Okay. Here is the Q value, very interesting, important definition. If I take a state, it can be a decay. A goes to B plus C plus D, or it can be a reaction. A plus B goes to C plus D. The difference in mass between the initial and the final state is called the Q value. And if you're a chemist, you know this thing as well. Chemists talk about reactions being exothermic or endothermic. We tend not to use those expressions in nuclear physics, but they're perfectly fine. We say that a reaction has a positive Q value or a negative Q value. Things which decay have a positive Q value because if they had a negative Q value, they wouldn't decay. Okay, just by conservation. Here's other conventions for mass. You can actually just describe the mass of atomic nuclei in AMU. By definition, carbon is spelled 0.000000. 0. Helium, although it's a very tightly bound nucleus, is very slightly greater than 4. So its mass excess, 4.00260 minus 4, the integer 4, is a positive number. What does that tell you about helium? Is it unbound? No, it's bound. It's just not as bound on average per nucleon as strongly as carbon. Okay. Now, when you get up a little bit heavier than carbon, and for reasons you understand when you see the curve of binding energy, all of a sudden you'll see for a very large swath of atomic nuclei, from around mass 16 up to somewhere around mass 200, all of a sudden the mass at AMU tends to be slightly less than the integer. That means to say that its mass excess, when you look it up in the nuclear data tables, is negative. Does it mean it's unbound? No, it means it's bound, but just not bound quite as tightly on the average as carbon 12. Binding energy is another way of describing the mass. It's not too convenient, and we're not going to, rarely will you do this. I may have you do some 1 or 2 exercises, but that's it. All right, just to exemplify the point I made before, doesn't work. Okay. It's not essential, but you have a. The Korean Army is always ready to fight. Ready to fight tonight, right? Good. All right. Thank you. Here we are. You see, up through carbon, the mass excesses, you can see, are going to end up being positive because the numbers are slightly larger than the integer, even a little bit beyond that. All of a sudden, when you get down to oxygen 16, all of a sudden you find that the mass excesses, again, we set carbon 12 as kind of the standard here. All of a sudden, mass excesses are negative because the mass, the atomic mass in AMU minus the number itself, 20, is slightly negative. And it's negative, 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 negative. And even up here, here's lead 214. And then all of a sudden, you have a situation where here we are with radon, all of a sudden, we find that the mass in AMU once again is slightly larger. So all of a sudden we have a positive mass excess here. You're bringing at the picture, if you've done your course with Lee Bernstein, you know exactly what the picture is going to look like here. We'll look at it in just a second. Now, this is where I think we stumbled before. It's actually important I to be able to scroll this up. How do we do this? Touch that? Okay. Good. Make this a full screen. Not essential, but yeah. Good. All right. Now, this is a really cool web page that you should become familiar with, and you'll need to do it for if I give you a problem on the problem set. This is from the NNDC, the National Nuclear Data Center in Brookhaven. Lee Bernstein, this is part of the National Nuclear Data Program, of which there's probably about 10 hubs. Professor Lee Bernstein runs a very large hub here, the joint Berkeley campus work for that. So let's actually play with this. I actually find it's a lot of fun. Notice when I scroll over this, I actually see the isotope. So let's take a look at carbon at the alpha particle, which is helium-4. Helium-5. There's helium-4. I'm going to click on it. And now, okay. Okay, now you can say, well, I can't see too much. So I'm going to hit zoom. Now, when you hit zoom, it zooms into the place that you clicked. And now you see a little blue box around helium-4. which is an alpha particle. Now, look down at the bottom. And right there, it will give we'll talk about this later on, unimportant right now, the ground state spin parity. Here's the delta, which is, as we said, 2.429 MeV. Where did that come from? Well, it came from okay.
The one that was four.
There, okay. So it's the mass in AMU minus the integer number times 931.48, which is the 1 AMU. Notice that this is smaller by about 7 or 8 MeV than the mass of the neutron and the proton being 938 something and the neutron being 939. So at something like 6 or 7 parts per thousand, an AMU is lighter. And of course, that's true because remember, carbon is a bound nucleus. If I take 1/12 of a bound nucleus, I'm going to get a mass which is slightly lighter than the bare proton or bare neutron. Now, if you recall, this thing was 4.0028 or 6, I think, minus 4, so that's 2.6 10 to the minus 3. And that's what gives rise to this number, 2.42 MeV. Okay, so now let's go look at carbon 12. There we are. By definition, the mass excess is 0.000. Now, here's something interesting. You can actually take your cursor here. Here's mass 12. Suppose I look at all kinds of nuclei that have mass 12, but different ratios of protons and neutrons. So let's take a look at O12, which is an odd beast. It's only made in nuclear reactions. It doesn't live very long. There we have it. Decays by proton emission. Notice that it has a whopping mass excess. It's 32 MeV. Let's go the other way. Let's look down here at beryllium 12. Once again, a very odd beast. It lives 21.5 milliseconds. It has a 25 MeV mass excess. So right in the middle, carbon 12 has 0. If I keep the same atomic number, whatever, upper left-hand corner number, okay, 12, and I deviate in proton-neutron ratio, all of a sudden the mass excess goes up steeply on either side. This is a lot of fun. Just make a cup of tea sometime and play with this. Let's take a look. Here's we'll go up. Here's uranium 238. Find uranium 238. Sometimes the best thing to do is just get into the neighborhood, click in, zoom, and there we go. Here's uranium 238. It has a mass excess of 47. It's one of these things, again, that has very large mass excess. It's a bound nucleus, i.e., it will not fall apart into 238 nucleons. But the average binding, the energy per nucleon binding clearly is worse off than carbon because it has a very large mass excess. Once again, if I take a crosscut at any part in the periodic table, and before we go, the other thing you'll notice down here is it actually tells you if the thing is unstable and decays. This will become familiar with. It'll tell you how it decays. It might decay by SF. It's not San Francisco. It stands for spontaneous fission. Alpha for alpha decay. Beta for beta decay. We'll talk about that just in a second. If there are multiple stable isotopes, it tells you which is the abundance of that one. There are some where you have several absolutely stable isotopes of the same element. And it tells you, this one is 13%, this one's 87%. And then the ground state half-life there. In this case, the decay lifetime of uranium-238 is coincidentally almost identical to the age of the solar system and the Earth, which is 4.55 billion years. Here you can see the half-life of uranium is actually 4.5 billion years, just total coincidence. But that makes it a nice chronometer for geologists, who study the history of the Earth's formation and development of the Earth's crust and so forth. Okay, so let's get out of this. So play with that, have some fun, familiarize yourself with it. Good. So, those of you who are hikers, think of the Valley of Stability, which is what the chart of nuclei is called. Think of it as like a topo map. And what we just did, we just did down here for a couple of places, but you can do anywhere up here. You actually find that the binding energy is largest here, i.e. the mass excess is always the lowest here. But if I now look at nuclei which have the same number of nucleons, but different proton-neutron ratio, it goes up steeply like this. So think of it as a valley, a very, very, very narrow valley. That's what you're looking at. And by the way, at some point, it stops. You cannot make nuclei of an unlimited size, except neutron stars for a special case. Why do you think the chart of nuclei just runs out? I can make things, by the way, as you know, Berkeley Lab, Lawrence Livermore National Lab, have a tremendous history pioneering the discovery of super heavy elements. We've actually found nuclei up to what atomic number now? Yeah, I think maybe 120. But there's a team from Livermore and Dubna in Russia that jointly over a couple of decades discovered 112, 113, 114, and so forth. Uranium is 92, plutonium is 94. So these things are, let's see. California is 99. Berkeleyan, who's got a t-shirt? What's on the t-shirt? Oh man, you pay so much money, you don't get a t-shirt. It's 97. Okay. And then the super heavy elements, these very exotic things that only live a nanosecond or so, but in some cases they live long enough to do nuclear chemistry on them, go all the way up to 118, 120 right now. But beyond that, we've not discovered stable nuclei. There's a reason for that. We'll get into this a little bit shortly. If something doesn't exist, it means, yeah, it's unstable. Why isn't it stable? It's the Coulombic force. It's they're also getting very charged, and of course there's a repulsion between all the protons, and that's what's driving up the excess energy. And at some point it just becomes unstable. It just immediately fissions. But we'll talk about that today. Here, I've just taken out of this, I'm old fashioned, I actually have the book. Okay, like Leonard Perlman, Jeff Belden, all the Virginia Shirley, and all these people that for years and decades actually maintained this large book with all the thousands of nuclides we know about. If I take a crosscut, it's exactly as I mentioned. Right at the bottom of the valley, you find the most stable nucleus. When I go up the sides of the valley, I find the nuclei become heavier and heavier and heavier. And what you're seeing on that scale on the left-hand side is the mass excess. It's roughly parabolic. In some cases, it kind of looks V-shaped more than parabolic. I'll have to ask Lee why that's true. There's a simple formula to tell you it should be parabolic, not V-shaped. But anyway, you get the general drift. Now, very simple question, it's a law of life. If one state has more energy than another state, what generally happens? Exactly. In general, if it's possible, if something has too much energy, that system will shed the energy. In the case of atomic nuclei, as the case with atoms, it's basically called decay. The way you get rid of it is one of several ways that a state, a nuclear atomic state that has too much energy, will shed energy. We'll talk about alpha decay, we'll talk about beta decay, we'll talk about fission, and so forth. And then you can actually see up there, some nuclei have these little arrows going down called beta minus. That means that's undergoing what's called beta decay. For how many, question?
When we're calculating delta, do we assume that N is the mass when the atom has all of the electrons?
Yes, that's right. And the reason for that is that, yes, that's right. Right. Yeah, so this is, so strictly speaking, it is the mass excess of the fully dressed atom. But because this would have, if the thing had the average binding energy of a carbon atom, this atom would also have the same number of, might be 60, it might be 24, it might be 12 or whatever. The electrons here canceled out, but you're right. And the masses, for whatever reason, in the table, someone in their infinite wisdom some decades ago decided those should be atomic masses, not nuclear masses. Okay. How many for you? This should be all be easy. Is this familiar to everybody? I'm boring you, correct? Good. Who's not bored? Okay, we can speed this up. Okay. No, we're doing fine. Okay, so let's calculate a Q value. By the way, last week I was incorrect. It's not today, it's next week that Mark Chadwick will be given a colloquium in the physics department, who's the grandson of James Chadwick, who discovered the neutron. And this is how he discovered the neutron. People had evidence that there were, he had already known about gammas, and he knew about X-rays, he knew about alpha particles, but we were seeing some other things that were very puzzling. And finally, Chadwick put his finger on it. He did this experiment where he took a source, just as Rutherford had done many years before, a polonium source that's emitting alpha particles. He collimated it into a beam. He put up a slab of beryllium, thin sheet of beryllium, and he got a reaction by which a helium nucleus, an alpha particle, 2 protons, 2 neutrons. This is 4 protons, 5 neutrons, became 6 plus 6 plus the free neutron. Everything balances here. Protons are conserved, neutrons are conserved, like that. And these neutrons went flying off. Now, neutrons by themselves, being neutral, are not easy to detect. You could not detect them in a Geiger counter. What does a Geiger counter count? What's giving you a really primitive description of a Geiger counter? That kind of gives it away.
Particle enters a gas, create some
gas.
ions.
Yep. So it's got to be a charged particle. Most generally, it's a charged particle. You get some gas. The charged particle goes in and it rips the electrons off the ions. You've got a voltage there, so the electrons will drift in towards the central wire, and then the negative ions will drift towards the outer wall, and you get a signal. But a neutral atom can't, a neutral particle can't do that. So what Chadwick has done, operating on a hunch, is if he thinks that a particle here can strike the proton and then knock the proton forward. The proton you can see easy as pie in a Geiger counter. And so that's what he did. And he sees a very, very big signal. That's how the neutron was discovered. Now, let's actually calculate roughly what that the energy of the neutrons coming out was. So mass excess of the helium-4, well, actually this is done just in AMU, so it's 4.0026. Go to the table, 9.012. You could have done this with the mass excesses, but this is what it looks like in written out as AMUs, which is the other way of calculating. 12 exactly, 1.0865. The difference between that is an AMU, but how much is an AMU? An AMU is 931.5, and out of that comes 5.7 MeV. That's a very, very typical energy for an alpha particle being emitted from a source. Why do you think, if he had some hunch, here's the thing that actually intrigued nuclear physicists at the time. They actually found that you have elements that actually have multiple isotopes. You actually found that you might have, for example, O16, it was clearly charge 8, but total mass of 16, plus a little bit. But you also found something that had charge 8 plus 10 protons, or 10 neutrons. What we know now is had a total atomic weight of very nearly 18. So there was a hunch in these experiments using spectrometers, these mass spectrometers, that in fact there was another component to the atomic nucleus with almost the same mass as a proton, but was electrically neutral. And so why do you think he picked paraffin for the secondary target? Who plays billiards here? Cool. Are you good? No, okay. What's one thing, if I strike one pool ball against another? They do bounce, indeed. What happens if I hit one direct head on? No. Yes. Right. For equal masses, the special thing about equal masses is that if I hit one pool ball into the other one, the second one takes off and the first one comes to a dead rest. Okay. In any other case, if I shoot a pool ball or a bowling ball, the bowling ball will have a slight recoil, but most of the energy will come back right at you like that. What's paraffin got a lot of? Hydrogen, right. So this was a very judicious choice because neutrons and protons have roughly the same mass. He could expect that many of those protons would pick up the full energy of the neutron coming out and give a robust signal in the Geiger counter. And that's in fact what he did. That's why paraffin, polyethylene, all this kind of stuff is a very good neutron moderator in nuclear technology reactors. That's why water is a very good moderator. It's because of the equality of the neutron mass.
How did Chadwick know the mass of neutron?
That's a good historical question, but as I recall, I think it's because of the fact that they saw for elements that had multiple isotopes, those isotopes had suspiciously integer-like masses to them. That began to, I mean, not a foregone conclusion, but you might suspect that there are other nucleons in there other than protons, but the electrons. That's the most, probably the most logical assumption you might make if you saw the fact that these isotopes had nearly integer masses. There were a number of very famous people who built, I think we'll show one later on in the course, who really built up the whole art of building very high precision mass spectrometers to measure the masses of atomic nuclei, even out to 3-4 decimal places. In fact, it plays a very interesting historical role. When it was discovered in 1938 that uranium fissioned, they knew that there were two isotopes there. They didn't know it was the fissionable one. They actually was able to measure and mass separate by the same means in a mass spectrometer, actually separate out the components of 235 and 238, and then test which one was the fissionable component. Okay, there's the money slide. This sort of encapsulates everything we've been talking about before. We noticed, so up here around 7.5 something is the average binding MeV per nucleon of carbon-12. We simply define this to be the average binding, okay? And we noticed something. We noticed that all the nuclei lighter than mass 12 and a few a little bit heavier than it, in fact, were less bound. These are things that had a positive mass excesses. From here all the way out to about here, they have negative mass excess, or excuse me, they have negative mass excesses, which means they're more tightly bound on the average per nucleon than carbon. It goes up to 8 and a little bit. And then there's a crossover point again here. But again, this was an arbitrary number, so that's the fact that it crosses over is really quite meaningless. But this curve, which goes up, reaches a maximum, and then slightly tails off, contains two extremely powerful messages. By the way, here's iron, which is the iron and chromium region, which is the most tightly bound atomic nuclei. These become successively less unbound because they become more highly charged, and the internal repulsive energy of the nucleus is actually trying to break the thing apart. So there's two ways of making money. Here, I can take light elements, fuse them to make heavier elements, and I get energy out, right? And that's why if I take tritium, which is hydrogen 3, plus deuterium, hydrogen 2, I can make alpha particle, which is a special case. It's a very, very, very tightly bound nucleus, plus a free neutron with a lot of energy, 14.1 MeV. Total Q value is about 17 MeV in that. So fusion allows me to take lighter elements, make heavier elements, and I earn a profit. The other way I make money from this is I take very heavy things which are very unstable in the mass 200 range, and I split them apart because the energy, it turns out two nuclei of roughly half the mass of uranium are each more tightly bound on the average than uranium itself. And there you get a humongous amount of energy, about 200 MeV per event of fission. In fact, you can see that number right here. So let's see that number. Yes. So for uranium, right here, you see the average binding is on the order of about 7.5 MeV or so. When you get into the middle here, you actually have, actually it's closer to 7, 7.25, 7.5 MeV per nucleon. Up here, if I split the thing into two parts that might be mass of 90 and mass of 130, you actually find that the average binding of those nuclei is about 8.5 that means I've gained per nucleon 1 MeV per nucleon in uranium. That's a healthy return on investment. Okay, so you didn't invest anything. So basically, 200 nucleons, by breaking it in half, I ended up with 200 MeV. Because the average binding per nucleon in the 2 daughter nuclei is a full MeV more. They're more tightly bound by an MeV per nucleon. Okay, that's where the humongous energy of fission comes from, and then why we are able to have power reactors in nuclear weapons. Okay, so that's the money slide. Okay, final point here, and I'm actually going to begin a little bit in the next lecture as well. I want to take a pace here slightly. I think you know that even before the quantum mechanics, even in the late 19th century, early 20th century, before it had any distinct idea about the atomic system, people who took diffuse light, like the sun or something like this, and broke the light up in a diffraction grating or a prism or something like that, actually found that sometimes they would see light in a continuum, but they would also see very sharp emission lines. And they had these very fascinating, I mean, scientists are puzzle solvers. They actually found the kind of a very unique set of transitions that seem to obey a kind of a mathematical pattern. I mean, that's like giving a jigsaw puzzle to an inquisitive child. I mean, physicists love this. And they actually found kind of empirical relationships for the series of these spectral lines. And this was the kind of thing that was grist for the mill for the people who would ultimately develop the quantum mechanics and the atomic theory that derived from that. Niels Bohr, of course, made up a very simple picture pre-real quantum mechanics in 1916, where he was able to explain the level diagram of hydrogen. So we actually had a fingerprint for all the atoms. So you could put these things, you could keep them, you could take them into gas, ionize them, or you could put put them on a hot wire and heat them up. You could actually look at the fingerprint for all your basic chemicals and see the spectral lines associated with every atom. As the atoms got larger, the spectra got more complicated. There was actually one atom that was actually discovered elsewhere than the Earth before it was discovered on Earth. What was that? Helium. Anybody here was an undergraduate at Johns Hopkins? Okay. If you ever go to the physics department at Johns Hopkins, in the foyer, you'll actually see a beautiful glass case. This was the institution of Henry Rowland, who was very, very famous. He actually made this precision machine. It's like a precision automatic lathe that was known as Rowland's ruling engine. It's something that made scribes on a metallic substrate extremely precisely. So he's the guy that made diffraction gratings of incredible precision. And he was the one that actually took a spectrograph, looked at the sun, and actually saw evidence for an atom that had never been seen on Earth. And that atom was named after the sun Helios, whose name Helium. Okay. That's Henry Rowland. Okay. So I don't want to make a big deal about this, only to say is that just in the same way that atoms can exist not only in the ground state, and everything we've been talking about so far, the NMC will give you atomic or nuclear level schemes as well. But when we talk about the mass excesses, we've normally been talking about the ground state here. Nuclei, in a similar way, do not exist in a whole sphere of excited states. They only exist in discrete states, and this comes from consequences of the quantum theory. And so here is, who is this? This is polonium-211. No, this is not polonium-211. This is carbon-12. First excited state is very high, 4.4 MeV, 7.65, and so forth. Here's polonium. it's got a ground state which is not integer spin, it's 9.5 plus state. Astatine on the right. That's all I wanted to show about that. Okay, here's our toolkit for lecture 2. You've learned a few more things today. You know that atoms tend to be about an angstrom or so, 10 to the minus 10 meters, 10 to the minus 8 centimeters. Characteristic energies, as we saw before, are measured at EV to the KeV range. Nuclei are 4 orders of magnitude smaller than that, and the kind of the currency of energy levels, the atomic nuclei are in hundreds of keV, tens of hundreds of keV, up to tens of MeV. And as you saw, the Q values for reactions compared to chemical reactions are a clean 6 orders of magnitude higher. And radii of nuclei, they're small, they're compact, 1.4 to the cube root of the atomic integer describing what the thing is. And that tells you the radius of Fermis. For the very heaviest nuclei, it never gets more than about 8 or so. Uranium, that's maybe about 8 Fermi. Oh, value proposition. But if you're a nuclear engineer, I'm not telling you anything. So, 1,000 megawatt power plant, 250 trains, you know, so that's 25,000 train cars per year of coal, 11 super tankers of oil. Okay, these are bad news. Fission would only take 1 rail car per year. And for fusion, it would be a couple hundred pounds in the back of your pickup truck of lithium, which you can make tribute. And there's planets at the bottom. Now, you're not going to go watch Chernobyl 46 over Okay. Okay, we're done. Bring up the next one. Yeah. Any questions on this so far? This should be all old hat to you. And those of you who are not science and engineers, you're going to be fine. These guys are going to take care of you. Simple stuff. So we talked about the fact that if you have the system which has 2 possible states of energy, it will obviously go from, it will try to go from one to the other. There may be reasons that something is not permitted to decay, but generally it can. In fact, the old adage in physics is anything that is not forbidden is mandatory. So in other words, if there's no what's called a selection rule or no conservation law that forbids the decay, then eventually it will happen at some point. So let's actually talk about decay right now. We'll get a little ways into this lecture in 8 minutes. And then we'll hang it up. Okay, radioactive. We'll give you the ABCs of this thing here. The ABCs of this. Okay. We talked about Chadwick. We've talked about alpha decay. We talked about Rutherford using alpha decay in the days before accelerators. This was the way it can fast, swiftly moving ions that you can use as probes. Roughly, when was the first man-made accelerator made? There were about 3 inventions, all in the space of a few years. All in the space of about 3 years. No. CERN didn't exist until the 1960s. Berkeley was early, yes. When was the second one invented? You ever see a picture of the first one? I think it's even in a museum here on campus. About 1929, 1930, I think, was the invention. It was like building a ship in a bottle. We actually put 2 kind of D-shaped pieces of metal. They're actually kind of hollow on the inside. So it's actually like a little flattened tin, except it had a cut in the middle. You could alternate the voltage between the two. And he actually built this thing inside an Erlenmeyer flask and then heated up and flattened the flask and then pumped on it. But basically, it was like building a little ship in a bottle. So the first cyclotron was about this big. And then this next one was 12 inches. They kind of exponentially went up and up and up. You saw this, of course, into there. Trinity, at some point, everyone was very proud of him, but he was making quite a bother on campus because his buildings got bigger and bigger with shielding walls, radiation, and so forth. He told him to take his pack up the hill and start a laboratory there. Yeah, that was there is a machine, electrostatic machine called the Dutch name Van der Graaf, by my alma mater, Robert J. Van der Graaf, invented in 1931. So, no, it's not. 1929. At MIT, they have on the Charles River a museum of science there, and they actually have one of his original Van der Graaf generators. I'm sure you've seen these things. It's quite a prodigy. It has a large dome. Of course, modern Van der Graafs don't look like this anymore. A large column like this, the base with a motor. Like this, and he actually has a pulley with a belt, kind of an insulating belt of rubber, very wide. And they run this thing at high speed. And he has a little brush here that picks up the charge, and charge is sprayed on down here or just taken off by friction, like this. This gets up to several million volts. But the interesting thing about this is that this thing is that big. It's really enormous. Actually, his first Van der Graafs, some of his early machines were like 60 feet tall and made real lightning bolts and so forth. They're quite the thing. You can still see them in Boston at the museum. Nowadays, Van der Graafs tend to be horizontal machines. The Pelotron is a derivative of the Van der Graaf. We have one in the basement of Echeverry. You've seen it. We call it Postman's Folly. He's trying to get this thing fixed. I keep trying to get it to throw it out. Ed Morse brought it in like a cat bringing in a dead mouse into the laboratory 10 years ago. Never worked properly. But it actually has the charging belt going horizontally. In this case, it's a metallic chain, and it gets up to about 5 million volts. Like that. And then this is now useful because you can now use this to accelerate a beam and make a variable energy high current beams of anything you want, electrons, protons, particles. The earliest one that beat both of those and actually made a nuclear reaction was by Cockcroft and Walton in the UK. I think around 1929, 1930, something like that. It was, and if you're an electrical engineer, I just simply make one of these, what are they called? You make it of diodes. It's basically you just put AC in and you just build up a high voltage on top of it, sort of like a diode transformer. And they actually use that to accelerate a beam, actually make nuclear reactions for the first time with something other than natural gravity. And then, of course, they accelerate very well. So here's the alpha particle, alpha decay. As I mentioned, if you look at the energy of alpha particles coming out, they come out in discrete energies. Okay, now they may come out. Sometimes of these decays will come out only one energy for a nucleus. Sometimes, in the case here of plutonium-239, you actually see there's 3 lines: one predominant line, 2 others. Typical alpha decay energy is about 5 MeV. Now, what happens? I have a nucleus that goes from A and Z. Okay, let's say 238, uranium 92. The alpha particle is the helium-4 nucleus, and this is going to be, now I'll embarrass myself. That's probably 234, right? Thorium? That would be 90. So I'm now zooming in. I just made a screenshot of the chart of the isotopes here. There's plutonium 240. So it's going to alpha decay. And I always, for people who've not done nuclear physics before, I get them to think, well, think of the chart of the nuclei as a bit of a chessboard. And you're on a chessboard, each piece has its own way of moving. In this case, alpha decay does what? Right, goes diagonally down and brings you to 236 uranium. Like that. So mass is conserved, charge is conserved, but I now go from something that's 4 mass units higher to something with 4 mass units less. And you see it's actually lost 2 protons and 2 neutrons. Okay, beta decay. And then we'll hang it up. Let's see what we get. Beta decay is typically, there's a few variants of beta decay, but in general, if I have a tritium, for example, hydrogen-3 going to helium-3, it actually gives off 2 decay products plus the recoiled daughter nucleus. And here's nitrogen-14, for example, or the daughter. This is carbon-14, which is a chronometer, very useful for people who do geology and other things like that. So it actually has a state of greater energy than nitrogen-14. So how does it shed energy? It'll emit an electron and an antineutrino. The fact that it's a 3-body process, if something decays as a 2-body process, and it has a certain Q value, then conservation of energy and conservation of mass deterministically tell you there's no degrees of freedom, that they go out back to back, and that particle will have a sharp energy. If now you have a 3-body final state, there's an infinite number of ways they can share that energy, and therefore you get a continuum of energies there. Very rarely will the electron take all the energy and antineutrino take none of the energy. Don't worry about antineutrinos, it's actually too important in this course. So here, how does, this is a chessboard. How does the beta decay? Run a little here. Oh, let's get some new players here. Oh. All right. Goes up. Where are? What stays the same? The number of nucleons stays the same. Let's hear from the Navy in the back here.
I think I thought it went diagonally.
It does, exactly. Bingo, you got it. Like that. So think of it as a chessboard. Beta decay brings you diagonally up and to the left. And yeah, for the purpose of this class, think of antineutrinos as having no rest mass. They're massless. Because it's the 3-body final state, the energy of the beta is not charged. It's a Schmier. It's important across the whole chart of nuclei. It's not just for heavies. And the energy is given off for KeV to MeV. With that, let's stop for today and clear out the next.
Quick announcement. Real quick before you get out. Discussion section starting this week. As you saw in the announcement, it's 6 to 7 on Wednesdays. If you can't make that, I'm going to hold some informal office hours. You can also do discussion outside, right outside that window in the little patio area right now for 30 minutes.